Oh, welcome to lecture 18 of Math 2R03. Today, what we're going to be looking at is section 5.b on eigenvectors and its connection to upper triangular matrices. So let me just put my book away here. So just to kind of remind ourselves kind of what we did something back in chapter 3 earlier is that once we fix a basis of our vector space, and if we take a linear map, okay, in this case we're looking at the linear operator, then there's a matrix associated to T. Okay, so let me make myself disappear here, and we can then see a little bit more about this matrix. So just a reminder is that the matrix of T with respect to this basis is an n by n matrix that has the following form. So it looks something like this. So we have A11, here we have A21, and so on, all the way down to AN1, all the way over this way to A1N, all the way down to ANN. So we have this matrix. This is going to be a square matrix because we're mapping from V to itself. And we have that TVJ is given by A1J V1 plus A2J V2 all the way down to ANJ Vn, right? So just kind of reminder that the jth column of here is given by the coefficients that you get after you plugging in Vj, right? So down here we would have A1J all the way down to ANJ. So it's just kind of a quick recap of where we were before in chapter 3. So given any linear operator and basis, we get a matrix. So the goal that we want to look at, and it's not just so much the goal for this particular lecture, but it's kind of what we'll see kind of going forwards. Oh, I just realized I didn't finish writing this here. This says the coefficients. Popped into the jth column. Okay, so just to kind of re-say this, what is our kind of our goal here is, can we pick V1 up to Vn so that this matrix MT is simple. Okay, now simple isn't a very good mathematical term, it's a little vague. So by simple here, what we're going to mean is lots of zeros. Okay, so how many zeros can we get into our matrix? So somehow, if we can pick our basis where this matrix here has lots of zeros, then it's kind of a good basis because hopefully we can read a lot of information from the matrix with where it has lots of zeros. Okay, and kind of the matrix that we're going to be aiming for, at least in today's lecture, is an example of an upper triangular matrix. Now this is something you may remember from Math 1B03. A matrix is upper triangular if all the entries below the diagonal are 0. Okay, so as some quick examples of this behavior of some upper triangular matrix, I could have something like 2, 7, 8, 0, 0, 9, and 0, 0, 10. So these zeros right here are below the diagonal, so it would be an example of something that's upper triangular. And then more generally, you would have something like this, lambda 1, lambda 2, all the way down to lambda n. Over here are all 0 elements, and over here are any value, right? So here I'll put that down, 0, all zeros, and then the star can represent any value. Okay, so my goal, or our goal as a group here today, is kind of to show that if we take a vector space over the complex numbers, so this is another example of a result where we need the complex numbers, and it's something that doesn't necessarily work over the real numbers, that we can find a basis of our vector space so that this matrix MT is upper triangular. So that's our goal for today. And in order to attain this goal, what we need is a criterion for determining when a matrix has when a basis will give you an upper triangular matrix. Okay, and that's what the following theorem here says. If we take a linear operator and we have a basis for the V, then the following are equivalent. This is a basis that will allow our matrix to be upper triangular, so that's kind of our goal. And then the condition is when we take that basis and we look at where Vj gets sent, after we plug it into T, it ends up back in the span of V1 to Vj for j going from 1 to n. And secondly, the span of the first j vectors is invariant under the operator of T. So you first look at the span of V1. Is that invariant under T? Then you look at the span of V1 and V2. Is that invariant under T? So remember, invariant under T means that you get mapped back into that space. And that has to be true for each j. So before proving it, and actually we'll leave the proof for the next part, let me just give you an example of this theorem in action. So here's my linear operator, and this is it's defined by going from R2 to R2, and it takes the pair xy to 3x plus 4y, comma 5y. And what we're going to do is we're going to use the standard basis, and we're going to show that the standard basis actually works in this case. So what we need to do is we're going to check the second condition. Okay, so when we look at t of e1, right, that's t of 1, 0, we will get 3 comma 0, and that's definitely in the span of the vector 1, 0. And if we look at TE2, which is what we get when we plug 0, 1 into my function, I end up with 4, 5, and that is in the span of 1, 0, 0, 1. So because of we've satisfied condition 2, we have that the matrix M, maybe I'll put that in here. So condition 2 is satisfied, and so because this is this matrix associated to the linear operator, it has to be upper triangular with respect to this base. And in fact, it's actually easy to see what the matrix is in this case. It's going to be 3, 0, 4, and 5, which is upper triangular. So hopefully this example helps, and in the next part we're going to actually come back and we're going to prove this theorem right here. Okay, I will see you in the next part.